Every company is racing to put AI to work, but most of them have hit the same wall. And it isn't the one they're watching. It's not the model. The models are ready. The problem is data, getting the right information in front of an agent at the right moment, accurately, across cloud, on-prem, and edge, without copying your entire business across the planet to do it. This is Attimis OneBucket, the mcp-native data plane that tears that wall down. Over the next few minutes, watch 3 things: retrieval that gets smarter on its own, a cost curve that collapses as it scales, and a brand new region brought online in minutes. It starts simple. We drop a fresh SEC filing into the system, live. It chunks and embeds in the background while we work. Let's ask for some simple information that can be found in the 10Ks. What regulatory and compliance risks do major tech companies cite for their cloud businesses? OneBucket reads straight from source the way most RAG ships today as real documents. In this example, Microsoft's and Google's 10K filings. The problem is that single-shot retrieval makes a choice, and it misses Google's core cloud risk section. That's the retrieval quality problem nobody talks about. Now let's try the same question, but with multi-hop. We cast a wider net across the whole corpus first, see which filings dominate, then drill in. The system decides where to look, not the user. First hop surfaces Microsoft and Google filings. Second hop scopes straight to them. Now it reads the winning chunks through the West policy, and every one of those reads are cold fills, quietly warming the cache on the second site. No separate warm-up job. And the answer changed. Different chunks this time. Google's actual cloud privacy section confirms GDPR enforcement history across all of Google Cloud. The single-shot answer missed it, creating an inaccurate or incomplete response. Now, what actually crossed between sites? Warm reads were 90 milliseconds, cold reads were 470. Same policy, same client, same network. The only difference is whether that byte range had been asked for before. 5 times faster, and we touched no infrastructure. 11 chunks are now warm on the second site, the chunks these questions needed. Over 400 other chunks never moved. The NVIDIA filing has crossed 0 bytes. Data moves on reads, not on writes, and what gets read is a tiny fraction of what's there. Let's try a different question. What is the concentrated supplier risk for AI hardware? It's a related but new question, and Google's supply chain chunk comes back already warm, having been read in the first query. Now the data is served fast on a question that had not even been asked yet. The cache compounds. Yesterday's reads are ready to answer today's questions. Remember the NVIDIA filing we dropped at the start? It's ready now. 202 chunks indexed and replicated while we did everything else. Nobody waited. We asked the same question, word for word, but now NVIDIA is the top result. A filing that didn't exist in this system 15 minutes ago has already become part of the answer. The index replicates eagerly because search has to be consistent everywhere. The payload tiers lazily because it doesn't. 1 system, 2 replication behaviors. Now the numbers. 1 petabyte of RAG corpus, 3 ways. First, eager replication. Copy everything everywhere comes out to about $1 million a year. Second, a vector database holding the chunks in line, the way most production RAG runs today, about 1.6 million. Lazy tier, the way OneBucket does it, about $25,000, because most of a corpus is never queried, and what is, serves warm after the first hit. And that's not a guesstimate. Peking University measured it. 3% of documents serve 60% of retrievals. Cloudflare built a business on the same power law. We just moved it from web traffic to retrieval traffic. Here's the whole picture. 17 chunks of 2,500 crossed to the second site, only the bytes the questions needed. 90% of the corpus never moved, and the heat map says it in one image. Only 3 sections of a 10K drive over 80% of every query. The rest is cold by design. That's the full system end to end. A new filing live, retrieval that improves itself, and a cost curve that flattens at scale. You pay to move what you read. Everything else stays where it is. That's the architecture. Oh, one more thing. Let's stand up a brand new region, Tokyo. A new storage endpoint, then a new policy. Japan is the sink origin, with East and West as cache peers. It's an inverted topology. The whole activation cost of a new geography is a few minutes in a console. No new infrastructure, no engineering sprint. Configuration, not code. Now, same question as before, but routed through Japan. The Japan bucket is empty, so every read will have to fall through. First, let's confirm the topology. All three peers are visible, Japan, East, and West. Japan is the sink origin, freshly created and empty. First a discovery hop, then a focused hop, the same as we saw earlier in the demo. Then 6 reads through the Japan policy. Every one of them misses the empty Japan bucket and falls through to the East cache, serves from there, and triggers a lazy fill back to Tokyo. The system doesn't know it's crossing the Pacific Ocean. It simply queues the fill and serves the best copy it has. It's the same lazy tier dynamics with an inverted geography, no special Japan mode. And the cost shape is identical. First read across the Pacific, 470 milliseconds. Once Tokyo fills, 90 milliseconds for Japan local. And for a petabyte, about $25,000 a year. The same curve as every other region. A new geographic origin is a policy you write, not an architecture you rebuild. The bytes follow the policy. Activation is the easy part. Knowing what to refine is still you. That's the whole idea. The data moves only when it's read, and most of it never moves at all. Running AI at scale stops being something you fight and starts being something that just works. The right data, in the right place, with full control across every environment. That's Attimis OneBucket, the easy button for getting your data to your AI.